So this is going to be the first video out of 4 that talks about the precise definition of a limit. And in this video, we're going to specifically focus on the two-sided limit definition. Before I get too far into the definition, I do want to address some of the symbols that we're going to use in this definition. For example, our first symbol is an old one. It's the symbol n, which is just going to represent our desired x value or input. We're also going to use the capital letter L, which we normally use to represent our y value guess, what we think the limit is going to be. It's our output. It's the answer. The other one we have that we normally use is f of x. It's just representing our function or relation that we use. Now, I'm going to introduce two new symbols. So the first one is this kind of S-looking shape, or maybe you think it's a D with a curl. That's actually probably the most accurate because it is delta. It is the lowercase letter d in the Greek alphabet, and it's representing a small distance along the x-axis. We also have this backwards-looking 3, or perhaps it's a strange-looking E, which it actually is. It's epsilon, the lowercase letter E in the Greek alphabet. It's representing a small distance along the y-axis. Notice that both of these new symbols are both representing small, positive numbers that are representing distance. Now, the reason we want to learn this precise definition is because we're going to use this later on down the road to prove that a particular guess L is the correct answer. So we would make a guess and then use this definition to prove that that's actually the correct answer. This is also called the epsilon delta definition because we're going to use these two symbols and they're very specifically used here. This is the most common place to see them. Now, here's what the actual definition looks like. And I realize it's a little long-winded, but we'll make it through. So, let our function f of x be defined on an open interval around n. Now, it doesn't have to be defined at that specific number, so we could have, an open dot, a hole, an asymptote. We could have kind of whatever we want here at n. It just needs to be around n on both sides. So we say that the limit of f of x as x approaches n is the number L, written just the same way we've written it. The limit as x approaches n of f of x is L if for every epsilon greater than 0, so remember epsilon is a distance, we want it to be a small number, but it's got to be positive, there exists a corresponding number delta, also greater than 0, again, positive distance, such that as long as my x values are within that little range between 0 and delta, then this implies, that's what the arrow represents, implies that f of x minus L is also within this little distance, okay? Now, I understand, again, this is kind of a wordy or long-winded definition. It's got a lot of symbols that may not make a lot of sense right off the bat. But let's go ahead and kind of try to approach this from a more visual standpoint, so hopefully we'll get a better understanding of this, okay? So, I've got my little graph right here. This blue curve is representing my function, and here's n, my little x value, the input that I'm plugging in. And what I'm going to do is I'm going to follow this up to where it is on the function and then come over to the y value over here on the left. That's representing my output, my answer. That's L. Okay, so again, start at n, go up to your function, see where y is, this L value. And then what I'm going to do is I'm going to pick some epsilon that I think is a good measure of how far away I can be from this limit. So in this case, I added epsilon and I subtracted epsilon from L and I got this little boundary here. Now, the goal is that I want x values to land between these two y value boundaries. And so I'll give you the example first of a good one. So here, I started at n and I added and subtracted delta from it. And all of these answers, if I look closely at my curve, give me this green section. Now, this green section is entirely between these two y value boundaries, L plus epsilon and L minus epsilon. These, again, are my boundaries that I have to be in between. And this is okay because, look, all of my green curve is between those two y value numbers. Now, I'll give you a bad example, okay? Now notice, I put this in red so that you guys could see it. If I look at all of these values, these x values between n minus delta and n plus delta, I end up with some that are just outside my y value boundaries. They go above and below this boundary set by L plus epsilon and L minus epsilon. And this is bad. We don't want this. We want, again, all of our x values to end up between those y values over here, okay? Now, again, bad. We want them inside the boundaries. So, what the purpose of this precise definition of a limit is going to do is it's designed to hone in on the correct answer. It's describing how close x values and y values need to be to say, okay, I feel comfortable that this is the correct answer. Now make sure we start to look for every x value between n minus delta and n plus delta, because it has to be between L minus epsilon and L plus epsilon, just like this graph. Again, I want these x values to produce answers between these y values up here, okay? Hopefully this helps you guys better understand what these definitions are. I'll see you again in the second video.